Alright, you bunch of cucks, today we're going to be learning about refraction and refractive index. Let's go! When a wave meets the boundary between two mediums, some of its energy is reflected back into the first medium, and the rest transmitted through into the second medium. If a wave meets the boundary at an angle to the normal being a line perpendicular to the boundary, refraction occurs, where the wave travels at a different speed in each medium, with a change of speed usually, but not always, resulting in a change of direction. When the speed changes, the frequency stays constant, but the wavelength changes, due to the wave equation. If a wave bends towards the normal, it's slowing down, and therefore going from a less optically dense material to a more optically dense material, and subsequently wavelength decreases, like in light going from air to glass. If a wave bends away from the normal, it's speeding up and going from a more to a less optically dense material, and therefore wavelength increases, such as light going from glass to air. Light travels fastest in a vacuum. It slows down in other materials because it interacts with the particles in them. The more optically dense the medium, the more particle interactions, and therefore the slower the light speed. The refractive index of a medium is a ratio of its wave speed compared to that of the first medium, and for the absolute refractive index, the one usually given in questions, is when the first medium is a vacuum, and can be used as a measure of optical density, where the ratio of the speed of light in a vacuum, c, and the speed of light in the medium. So for example, light travelling in glass goes at 2 times 10 to the 8 meters a second, so its refractive index is that under 3 times 10 to the 8, resulting in 1.5 with no units. This equation can be rearranged accordingly. Since the refractive index of air is close to 1, as explained later, light entering glass will refract towards the normal, due to glass having a higher refractive index as it's more optically dense. When a light ray is refracted at a boundary between two materials, the light is crossing a boundary going from medium 1 with refractive index n1 to medium 2 with refractive index n2. The angle the incoming light makes to the normal is called the angle of incidence, noted by I, and the angle the refracted ray makes to the normal is the angle of refraction, noted by R. These four are related by Snell's law, where n2 over n1 is equal to sin I over sin R, which is equal to light speed of the first medium over light speed of the second medium, where also, since the speed of light in air is only a tiny bit smaller than in a vacuum, using the refractive index of c over c, you can assume the refractive index of air is 1. So for an air to material boundary, you can cancel n1 to get n is equal to sin I over sin R is equal to the speed of light in the first medium over the speed of light in the second medium, where the speed of light is noted by c. Where if you remember how the absolute refractive index uses the speed of light in a vacuum as the speed of light in the first medium, you can see how it links in this situation as a sort of substitute. This can be expanded with a light ray from a ray box going from air into a glass block, where tracing the path, as done in the practical before, which you should have all done well except me because ray is fucking useless, you can see the angle of refraction is smaller than the angle of incidence as light enters the block, since it bends towards the normal, with the opposite effect happening as it leaves the block, as it goes to a lower refractive index. That being said, if you trace the paths and measured the first angle of incidence to be, say, 30 and refraction 20, using Snell's law, you can find the refractive index via sin 30 over sin 20 equals 1.46, which is very close to the intended 1.5, and remember the use of sine. Finally, if you were to replace the ray box with a source of white light, the colours will disperse in the glass block and get separated from each other in the process of dispersion. This is due to each colour having a slightly different refractive index in the glass block, such as red being 1.5 and blue 1.51. For most materials, including glass, the smaller the wavelength for the light, the higher the refractive index, making the refractive index a function of the wavelength, dispersing each wavelength, with purple being bent the most and red the least according to this principle. And I'm done. Thank you for paying attention, and James still smells a poo.